Okay, so we're going to look at concavity today in this video. So I'm skipping to concavity because, well, the first section of this graph, the whole title of this section in this unit is looking at the first derivative, connecting the first derivative and the second derivative with the graph of f. Okay, so we have multiple tests that we're going to look at. The test that we have already looked at a lot is the first derivative test, and that's still going to apply. So the tests that we're going to look at are going to be the first derivative test. And I'm not going to repeat that. There are going to be some example problems that repeat in this section on that topic, but I am not going to repeat that. That's going to be for local extreme values. And where we're going to spend our time in this video is going to focus on concavity test. And then another video is going to focus on the second derivative test and being able to find local extrema from the second derivative test. Okay. Sometimes you're going to need to determine which test you need to use. And also you're going to find sometimes that finding the second derivative is too complicated and too difficult to find algebraically, and you're going to want to emphasis on the graph in this section. So those are kind of the major topics of this section. If you would like some more practice on first derivative tests, I could definitely do another video on that, but I'm going to focus today on concavity. So when I go to do concavity here, we're going to talk about some basics of what it means to be kind of concave up, concave down. So if we look at a graph like this, okay, and if I draw in a graph that kind of is cubic here, it's going to go like this, and then it's going to go like this. The easiest way is if the graph kind of cups down and the water would spill out, this right here, okay, so the water would spill out, this is going to be concave down. Okay, and right here, if you could hold water in it, it's kind of cupped, so that's going to be concave up. So that's your basic intuition we could work with, but we're going to come into some exact definitions. So if I were to say, where's the figure concave up for this cubic function, if this is the graph y equals x cubed, I'd say it's concave up from 0 to infinity, and then it's concave down from negative infinity to 0. Okay, so we do need kind of an exact definition of concavity. This intuition is fine, but here's our definition that we're going to work with continuity. Okay, our definition is going to say a function is concave up if the first derivative is increasing on an interval. Okay, and then we're going to say the opposite here, if it's concave down, if the first derivative is decreasing on an interval. Okay, we'll get into exactly kind of what that means, because the next part, for a first derivative to be increasing, we're going to have to kind of define what that is. So if a function has a second derivative, if a function has a second derivative, then we can say that y prime is increasing if y double prime is greater than 0. Okay, so that's where it's going to be functioning if the second derivative is positive. Okay, and then we can also say that if y prime is decreasing if the second derivative is less than 0. Okay, so Basically, our concavity test is going to be second derivative, okay? So we're going to be looking at our second derivative in the concavity test. So for concavity test, it uses the second derivative, and we have to be careful because we need to make sure if it exists, okay? So the second derivative may not always exist, and therefore we got to come up with another strategy. All right, so here's the basic gist of the test. The test says it's concave up if the second derivative is greater than 0, okay? It is concave down if the second derivative is less than 0, okay? So let's look at an example of this. Let's look at y equals x squared, okay? And then let's look at the derivative of that is y equals 2x, and the second derivative is y equals 2, okay? So we look at the graph of y equals x squared. We all know it goes like this, okay? And we can tell this is going to hold water, so it's going to be concave up. And we don't need to look at this graph. But we can we look at it right here and we say, okay, well, what interval is the second derivative? It's positive. We see right here that the second derivative is always greater than 0. So that means it's going to be concave up over the entire interval. So that means this graph is concave up over the entire interval. Okay, so let's apply this to a little bit more complicated problem. So here's the scenario.